Hey everybody, so this research paper is called Directly Aligning the Full Diffusion Trajectory with Fine-Grained Human Preference, and it's put out by universities in China, and then it's dated September 9th, 2025. First thing that I want to know overall about this research paper and talk about is this. Their method, they take the flux model, flux.1 dev, and then they fine tune the model. So they fine tune the model for 10 minutes, which is awesome. But they use 32 Nvidia H20 GPUs in order to do this. Like, uh, this isn't like you can do this on your home computer, right? So I want to make that like immediately clear up front within this. The costs to do this overall like aren't actually that bad, right? Because so like the this chip, the Nvidia H20, is like the China like only like it's only sold in China, and it's like a nerfed version of the H100, and then you can rent A100s for like $2 an hour, and then it's 10 minutes, right? You would need 32 of them, and then so that's like it's $64 to rent them for an hour. As long as you had all of that code, like if you had all of this ready to go, and you're only spinning that model like this up for 1 hour, it would cost you $64 to do it. If you did it right? If you bought these GPUs, even the H20s, they're $10,000 a pop, right? Uh, buying them would be $320,000, but renting them in order to get to this amount of performance would be $64. So highlighting that overall, let's dive into the paper. This paper, like it's got a lot of good stuff in it, right? So I can just essentially, I want to like read through this paper and then talk about it. So the abstract: recent studies have demonstrated the effectiveness of directly aligning diffusion models with human preferences using differentiable reward. However, they exhibit two primary challenges. One, they rely on multi-step denoising with gradient computation for reward scoring, which is computationally expensive, thus restricting optimization to only a few diffusion steps. So there's two things to unpack within this first argument here, right? First thing is that it only trains you're only ever like fine tuning a diffusion model on a few diffusion steps, just because of the fact that it's so computationally expensive, right? Even if you're fine tuning it on a couple of A100s and then you're doing that for like a few hours, you're like LoRa training, whatever your method is within that. You're not LoRa training for a few hours, but you're only training few diffusion steps, right? Like LoRa is specifically like low rank adaptation, right? You're specifically training a small portion of the model. Whereas this method overall, it trains like the entire diffusion model, which is important. And then it's also highly important within that not only does this method train the whole diffusion model as a whole, like every single layer within it, but it's also doing it in ways that are more computationally efficient than current methods. And the two big methods are PPO and GRPO. And then they compare this SRPO method that they create to both of those methods overall. Second thing within this is that they often need continuous offline adaptation of reward models in order to achieve desired aesthetic quality, such as photorealism or precise lighting effects. To address the limitation of multi-step noising, we propose direct align, a method that predefines a noise prior to effectively recover original images from any time steps via interpolation, leveraging the equation that diffusion states are interpolations between noise and target images, which effectively avoids over-optimization in late steps. I'll just read through here. Furthermore, we introduce semantic relative preference optimization, or SRPO, in which rewards are formulated as text-conditional signals. This approach enables online adjustment of rewards in response to positive and negative prompt augmentation, thereby reducing the reliance on offline reward fine-tuning. By fine-tuning the flux.1 dev model with optimized denoising and online reward adjustment, we improve its human-evaluated realism and aesthetic quality by over 3x. Few things to unpack here with number two, right? First of all, is what they're talking about here with the need for continuous offline adaptation of reward models. Like, so if you've ever played around with GRPO methods for training diffusion models, the very first step is that you do a LoRa training, right? So you do a LoRa training and then you do the diffusion training, which is just massively computationally expensive, right? And then so they're eliminating that first step. So not only does it eliminate a step overall within that process, but it eliminates a massively computational step within that. And there's other ways that you can go about that offline process, but they're 100% right within that, right? That there's essentially an offline preference training process that you're running with these methods with GRPO overall before you actually implement it, which is massively computationally expensive. And then the biggest thing within this, and I'm going to highlight it now, highlight it all throughout it, is that essentially this method overall doesn't rely on images for fine tuning, right? Like with typical GRPO, PPO, etc. Like no matter what LoRa, no matter what the fine tuning method is, you're utilizing images to fine tune an image diffusion model. Whereas with this instance, it's very specifically it's a text condition reward, right? So it's based off of essentially like prompt optimization, and then it's that reinforcement learning via prompt optimization and the model optimizing that way is what builds this out. And that's very significant, right? Because that training on actual images and back propagating all of that data, etc., is what becomes very, very computationally expensive within this, right? And then so again, it's 32 GPUs, but it's the fact that it only takes 10 minutes within this is very significant. Again, $64 overall, like is your rental cost if you did it right? If you set this all up right. And then they go into their method a lot more in depth here. And in depth into online reinforcement learning overall. All of kind of the existing methods, why their method is an improvement over it, better than it, etc. This is another one and another important element of this architecture that they talk about all throughout with this, which is mitigating reward hacking. So the proposed framework effectively mitigates reward hacking. Specifically, it removes the limitation of previous models that could only train on the later steps of diffusion process. Furthermore, we introduce a semantic relative preference mechanism which regularizes the reward signal by evaluating each sample with both positive and negative prompt conditional preference. Kind of the bottom line within this is that since they have full access to all of the layers and you're actually training all of the layers within this, you get to mitigate reward hacking within this. So they do it through a very simple way. If you actually read it through the research paper in here, what they're talking about within this first part within this is that they just inject noise over the clean image before it generates, and then so that allows it to essentially not reward hack, right? Not specifically lock onto that exactly because you're adding noise to it. And so that's their method within that. But the second part is an algorithm that they introduce, which is super cool. And they introduce a few algorithms within this paper. Then they also, this online reward adjustment is very significant, right? So this is essentially what the model is operating off of. That prompt fine tuning process, and then that's what allows them for that full online reward adjustment. Breakthrough in efficiency, they keep highlighting this, right? This 10 minutes of training, and they highlight it all throughout. But again, I'm just going to highlight it here again: 32 GPUs, and then figure it as 32 A100s, right, or 32 H100s, and then that's what it is. Which you only need it for 10 minutes, but there it is overall. And then so within this, they have related work, which of course, again, it goes deep into GRPO and PPO methods, and then just refining those and how this method is essentially better than that method overall. And then they go into this is essentially good to look at overall, right? This gives you kind of the first hint of the performance, so you can see kind of the standard base model compared to theirs overall. And then they have more examples here. Here's all of their experiments, and then this is where the algorithms start here, and then so they introduce the main SRPO algorithm overall. Their semantic guided preference with all of the math behind it. There's 5 algorithms in this paper. So next step for me would be to break down and dissect and then go deep into these algorithms and then reconstruct from there. But this paper is very rich in the content that it provides overall for someone who specifically works with image diffusion a lot. This is a super cool research paper to me overall. I can't wait to try this method overall. To me, that the computational savings and computational efficiency is like the bottom line within this, right? Uh, people that like when you get into AI, right? There's a GPU barrier when you work with LLM models, and then especially like once you get above like 7 billion parameters, like you start getting into like massive GPU barriers, right? It's hard to run it on a single. You really can't run it on a single consumer grade GPU at that point. That's the point where you have to go to like an A100, right? But then with like an A100, you're loading. I mean, you could load up like a 70 billion parameter model, no problem, etc., right? And then so it's like you kind of think that like the sky is the limit within that. But again, 32 of those guys is what you need just to fine tune this model, right? And then it's kind of it will throw you off a bit in that regard too, because from like if I remember right, the flux models are 8 billion parameters overall. And then so like again, I just told you that you could train a 70 billion parameter LLM model, and flux is 8 billion parameters, and then you can't train a flux model on a singular A100, whereas you could easily train a 70 billion parameter model if you quantize it a bit on a A100, right? And then so the big difference within that is these training methods overall, right? The fact that you have to train the math for fine tuning diffusion models overall is just far more computationally expensive for training the same amount of parameters overall. And then so the fact that they are cutting so much out of that is very significant overall, right? 32 H20s for 10 minutes is pretty significant. Again, less than $100 if you want to invest all in and you put all of the resources in it. Their benchmark results come out phenomenal. It's benchmarks. I'm not gonna say that their benchmarks suck. I've never seen one of these papers do that overall. And then here's the results, right? And then so you have the base model flux, and then they compare it to dance GRPO, which is the paper that introduced the GRPO method, and then compared to SRPO, which is their method, right? And then so you can see here. To me, it does. It kind of works into a good, better, best. The dance GRPO method, if you look at the middle here, and then they highlight that this is reward hacking, right? Like what you're seeing here in the middle, like if we look at these compared to these, some of these are less realistic overall, right? Like this one's better, like the astronaut's better for sure, but this is a good example of this woman, right? Like this woman, like this second one has what I would call, I like to call the mid-journey look. Same thing with this one, right? This is very much mid-journey look, right? And it's because the model reward hacks on literal colors, things like that, right? And then so if a model is reward hacking, it's going to have more reds accentuated generally within it. That's part of the reward that the models tend to like to gravitate towards, right? And that additional red to me is what gives that mid-journey look to a lot of these things. But so you can see here the bottom one, right? You don't have that plastic look to it, right? That plasticness is reward hacking. I can't stress that overall enough, right? And then so here they just give more examples, and then this is this is with different methods, right? So via clip, via pick, via HPS, and then via AE, and then you can see this quality is very cool to me overall, right? This is a very nice, exactly what I would be looking for overall within this. And then so overall, super cool research paper to me. Everything about this overall is fascinating, great research paper. Lots of algorithms within it. This SRPO method is fantastic overall to me. It's very computationally efficient, and the fact that they're blending it all together, and they're not utilizing images. They do also provide an offline SRPO method. So if you do want that, they do test it out, right? And they put it right here at the very end. But so here's the research paper overall. I'll leave a link to the research paper here. Generally speaking, I like to go over code on these things, right? But again, I can't highlight enough. If there's no reason to give you any sort of Colab code when we're talking about something like this, and going through it, right? and then you have to, like, even if I gave you the code straight up for this, like, you have to figure out how to load balance and accept. Like, there's a lot, like, the preparation going into training on 32 GPUs is very significant, right? More significant than the actual training process itself overall. And it's the best way that I could put that. And then so you can do it again for like less than $100, but you're gonna put like hours, weeks of time into it before then. And then so overall, if you like this type of content, please like and subscribe. Thank you very much.